Today's class is about equilibria, the reaction quotient. The reaction quotient is a number obtained by substituting starting reactant and product concentrations or partial pressures into an equilibrium constant expression. The resulting value allows one to make predictions about how the reaction will proceed. If the value of Q equals the equilibrium constant, we know the reaction is at equilibrium, so no further change in concentrations of either products or reactants will take place. Although the reaction is still occurring, it's in a state of dynamic equilibrium. If, on the other hand, the value of Q is larger than K, then the reaction moves to the left. And if the value of Q is less than the equilibrium constant, then the reaction will tend to move to the right. Rather than remembering all these facts, one trick we can use to remember it is that the arrow for the greater than symbol is pointing this way, therefore the reaction the direction of the reaction flow will be that way. So the arrows are either pointing together or pointing apart. That's the best way to remember this little expression. An example of how we would use the reaction quotient is shown in our textbook on page 646. This is from Brown and others, 10th edition. We show the sulfur trioxide decomposing to sulfur dioxide gas and oxygen gas. The equilibrium constant is 0.338. We're given all the conditions of all the concentrations of the various products and reactants. This is the equilibrium expression. That's how we calculate K. We also use the same parameters to calculate Q. We plug in the numbers that we're given, and it gives us a value of 16.4. That's the value of Q. Q is larger than K in this case, and that tells us that the reaction is going to move to the left. So the interpretation of this result is that since 16.4 is bigger than 0.338, the reaction moves left to produce more sulfur trioxide. The reaction quotient indicates a reaction that is product rich, if you like. In the second example, we are shown a calculation where one of the products is missing. We don't know what the concentration of the second product is, but we know everything else. So we can set up an equilibrium expression. We know the value of equilibrium. The only thing that's missing is this, the concentration of Cl2. We assign it a value of x, do the algebra, and we get the resulting concentration of chlorine gas at equilibrium. In the next example, also obtained from your textbook on page 649, we have the same reaction, phosphorus pentachloride gaseous reacting, decomposing to form phosphorus trichloride and chlorine gas. We're given only one piece of information, well, two pieces of information. The initial atmospheric pressure in the sealed vessel of the phosphorus pentachloride and the value of Kp. We know that a certain amount of the PCl5 is going to decompose to give those two other chemicals. We're going to call that amount x. So at equilibrium, we're going to have 1.66 minus x of the PCl5. And likewise, because the reaction is 1 to 1 to 1 stoichiometry, we know that if 1 mole of PCl5 decomposes, we'll get 1 mole of PCl3 and 1 mole of Cl2. So if the initial concentrations are 0, or if the initial pressures exerted by those two gases are 0, we'll know that they'll increase by x. And the final equilibrium pressure will be x for both of them. So we can set up an equilibrium expression where it's product over reactants for the calculation of Kp. We enter the values we don't know, x and x in both those cases, and 1.66 minus x for the PCl5. All of that has to equal 0.497. When we do the algebra, we find that the only way to solve it is to use the quadratic formula, where the values of a are written over here. When we solve for x, we find that it's 0.693. You'll notice that there are two possibilities when you use the quadratic formula. One of them is positive and one of them is negative. We can't get a negative quantity for x, because if x is a negative number, minus x would mean that we're adding to 1.66. It's impossible for PCl5 concentration to increase because it's already starting out with only PCl5. So what it can only do is degrade. There are no products to revert to PCl5. So the only logical possibility is going to be a positive value of x. that has to be subtracted from 1.66. So whenever we do that calculation, we have to reason the answer through. We don't just blindly put down numbers that make no sense. The negative value of this answer is illogical and therefore has to be discarded. So there is only one logical answer, the 0.693. X equals 0.693, which equals also the concentration of PCl3 and Cl2. So 0.693 atmospheres for that. And the 0.693 is going to be subtracted from 1.66 to find the concentration of PCl5 that's still left over. And that gives us 0.967.